Take it away.
Thank you very much. So I'm Sander Devriendt. I'm a PhD student from KU Leuven. So this is a work together with my promoter, Professor Antonio, and my colleagues Tom Rakens and Roel Verbelen and Professor Jet Vries from Wisconsin University. So I'll talk to you about sparsity with multi-type Lasso regularized GLMs. So I'm actually a mathematician, and I'm now working on applied mathematics in an insurance context. So I'm used to going to actuarial conferences where there's like at most 10 to 20 people in a room. So if you'll be nice to me, I'll promise I'll be nice to you and don't show you too many formulas. So that's the first promise I'll make. Just to start right off with some motivation, I'm working in an insurance context. So what we're looking at here is basically a motor third-party liability insurance. So suppose I just graduated from actuary college at KU Leuven, and I want to get a car, and I need a car insurance. Well, I go to my insurer, and my insurer asks me everything that they want to know. They want to ask, what's my profession? I'm a mathematician. What type of car do you have? Where do you live? Which province of Hungary do you come from? How long do you have your driver's license? What's the type of fuel of your car? What's your age? What's the power of your car? This and that. So they ask all of this information. And the important thing to note here that all these variables have different structures behind them. You have something like profession or the model of your car, which is a nominal variable with just many, many levels, or you have the age of the policyholder or the age of your driver's license. That's a clear ordinal or a numeric variable. And then you also have spatial information or whatever type of variable that you have in your data set. So this is an important thing to take into account, because this makes our data problem difficult. Because what we want to do is we want to predict which policyholders will have a car accident and how severe that car accident will be. So from an actuarial perspective, what they usually do in companies is they want to fit a generalized linear model. They have several good reasons for that. The most important reason is what they call the actuarial comfort zone. It's what they have always worked with. It's what works with the regulator. It's what is interpretable, what you can communicate to the customer. So that's something that they want to do. So that's our focus for today. We'll work with generalized linear models. But then the question is, we have all this different data coming in, but some variables might be uninformative, might be not important, so we need to know that and need to find a way to remove them from our model. And then other variables, such as the profession or the model of a car, they have many, many, many levels. And we need to know which levels are actually similar enough to fuse them together. So these are our two main questions. And the goal of is to solve these questions with a procedure that is data-driven. So we're only looking at data and not at professional expertise or something. And it should be scalable to big data, definitely, because more and more data is coming in at insurance companies. Another way to rephrase this question is, with all these variables coming in, we should find a way to avoid overfitting by just plugging 1,000 parameters into your GLM. And we should find a way to avoid underfitting, where we a priori select our risk features without using data, and we're actually not using all the information that is there. So we need to find the optimal middle ground here. A first approach that our research group applied through my colleague Roel Henkaerts was actually a stepwise procedure where they did the selection upfront through an exhaustive search with a generalized additive model. So you already see here that doing an exhaustive search with best subset selection and stuff like that, this will not be scalable. But then after this first step, they use clustering algorithms for spatial effects and evolutionary trees for the one-dimensional effects. And with all the clusters obtained, they can finally fit, they can put these clusters into a GLM and fit a standard GLM context that works. They use these packages, but just to show you how that looks, they first fitted the GLM, which for an interaction looked like this, and for the spatial effects look like this. And then they applied a clustering algorithm or evolutionary trees and plugged that into a GLM, and then they get results like this. So then you have a clustered cross here, and then people with higher ages but higher powered cars, or higher ages and lower powered cars, they will have different GLM coefficients in your model. But we want to do better. I already told you that first step with an exhaustive search, that's not scalable. We want to do it in one step. We want to have it scalable. This is our goal. One step, less is more. So how will we do it? We will use regularization. What is regularization for the people not familiar? Well, if you have your standard linear model or your standard generalized linear model here, what this model tries to do is you give it data and it will fit your parameters as good as possible to your data, such that you have the best in-sample fit. That's what GLM or a linear model does. So there's no constraint on the parameters, you just want to fit your data. What regularized regression or regularized anything is about is you put a constraint on your parameters such that you get a trade-off between this in-sample fit, this in-sample data that you're trying to fit, and the interpretability of your model in the end. So you put a constraint on your parameters so that it's not too many parameters or not too far away from each other, and you want to improve the interpretability of your model. So first classical way, some of you will definitely know about it, is the Lasso regression, where you basically say, okay, this is my first slide with formulas, by the way. If you have a likelihood to optimize, instead of just plugging this into your GLM, you put a constraint on that. Here it is the L1 norm of your parameter space. And the idea is that by putting this constraint, you will actually put some parameters to 0. And if you look at this from a graphical point of view, this is Lasso regression. If you remove this octahedron, then you're doing a classical GLM or a classical linear model. Basically, your optimal parameter could be anywhere in this room, anywhere in space. But if you put a Lasso constraint on that, you're basically saying my optimal parameter for my model should be inside this octahedron. So you're putting a constraint on your parameters. And in this case, that will mean that some parameters will be put to 0, such that there is more budget, more room for the other parameters to capture the effects of your data. So that's regularization from a budget point of view. So how do you do this in R? There's a very good package, GLMnet, which you can use for Lasso or rich regression if you want. And the basic idea is, if you look at this formula, you have this lambda here, which basically is inversely related to the radius of your octahedron. So you can choose how big your octahedron is in space. And if you increase your lambda, that basically means that you put a more severe constraint on your parameter space. And if your lambda is 0, then you're basically doing no constraint at all. You get your GLM or your linear model fit. And if you increase your lambda, you see that your parameters, which are the lines here, they will get closer and closer to 0, up until the point that your octahedron is so small that just everything is in the origin. That's Lasso regression. So remember my talk about overfitting and underfitting. If you have a too big lambda, too much constriction, then you will be underfitting. If you have too small of lambda, you will be overfitting. That's the whole idea of regularization in my point of view. So, but we're not there yet. So I talked about regularization, but I also talked about all these different types of variables. And we saw from the previous plot, what Lasso does is basically it selects parameters. It's possible to put parameters equal to 0 with some value of lambda, but it will not fuse them together. It will not take these different levels and see which ones are close to each other. So for that, we need different types of penalties, and that's what we call the Lasso and friends in our case. So what we will do is we have our nominal type of variables. We will assign a specific penalty to nominal types of variables. We will assign another penalty for ordinal information, like age or the power of a car. And then for spatial information, we also allow different penalties. That's something that is usually not done in packages. They only look at either I do Lasso on all my parameters, or I do fused Lasso on all my parameters, or something else. But we need a combination of this due to our data having all these different types of variables. Okay? So how do I visualize these different penalties? It's actually, if you looked at this octahedron, that's just one constraint that you can put on your parameter space. If you take different penalties, then it's just your constraint will just look different. But again, you each time have like this radius going out. That's directly inversely related to your lambda parameter here. So that's a tuning parameter, classical in machine learning, that you need to find a good trade-off between over and underfitting. So this is an example of how group Lasso looks like, and this is an elastic net, and figures are actually from a very nice book on these Lasso type models of Hasty and Tipshirani. Okay, so this is an example of fused Lasso. So Lasso was about selection of parameters. For fused Lasso, you can see that it's actually fusing levels of parameters. So it's only parameters which are right next to each other, like 4 and 5 are fused here, or here it's 6 and 7, so the cyan and the blue line. And you see variable 1 is not right next to variable 6 and 7, so it's actually at a certain point close, but it's actually just crossing and fusing with another one. So fused Lasso is good for ordinal variables because there's clear ordering, and you will only fuse, like for the age variable levels, age 18 with 19, 19 with 20, 20 with 21, and so on. And you will not fuse like age 18 with 8t. So that's a good thing to know. So fused Lasso is a classical ID for ordinal variables. And then for generalized fused Lasso, that's basically for nominal variables where every category can be fused. And then you see, for example, that variable 1 and the sign variable 6, they can be fused together. So it's just to show that all these different penalties exist. The only thing we need to do is be able to combine them, that we say, but I want to apply a Lasso on these 3 parameters, a fused Lasso on these, generalized fused Lasso on this, or elastic net, or a scat penalty, or something else. That's something we have to do. And the first solution to this problem, like with these different types of penalties in the same data set, in the same objective function, was solved by a research group in Munich by Gert Huijsen-Toets and Ulker. And they found a way to do this for GLMs. And they put it into an R package. So when we started this research, we were very, very happy. As we have an R package, we can just use it. But when we started to use it, we noticed there were some bugs. It's also not maintained anymore because their PhD student who built it moved to a company and just didn't look after it anymore. But there's another problem with this package, and that's basically the optimization scheme that they use for this problem. And they use local quadratic approximations, which basically means instead of fusing this exactly, they will just stay close to each other and move along a line close to each other. But then you get this extra problem like, okay, how close should they be before I fuse them? Because if you fuse them here, that's not correct because it's actually going further on. So you need to have already an idea of what you're doing there. And also, the whole computational thing is actually putting everything in one big matrix, so that makes it also not so scalable. And the bulk of our research actually went into finding a better algorithm to fit this. This is basically where my research came in. And we found a nice and efficient algorithm with proximal operators. It's very, very technical, so I'm not showing you that. But this, I implemented it together with my colleague Tom Rekens in C++, which is a very nice thing to do if you want to optimize your code. It runs way faster. We also used a lot of other packages to optimize it and some theory from proximal operators. But the big idea is our algorithm does exact fusion, so it's not doing approximations up to computer precision, of course. And it's actually scalable to big data because we're able to split our objective function into its parts with the different penalties, and then we can use specialized algorithms for each of these penalties. And because we can use these different penalties, it's quite a flexible regularization. So we're building a package on this. It's in the final stages, so we hope to get it out in the next month or two. And if you're interested in it, you can just contact me and I will put you up on a mailing list and make sure that you know about it when it's out. But I think the most interesting thing is to see how it actually does on the data set. So I have a data set here. It's motor third-party liability insurance frequency. So we're only modeling the claim count. So how many claims does a policyholder have? We have 160,000 observations. We have 14 variables, binary, ordinal, nominal type of things. We have an exposure, which we model as an offset, and we just fit a Poisson GLM. So because it's a count data, Poisson GLM is very nice to do. And we have our objective function here. So we have these 14 variables, and each have a list of levels. So you have like the gender only has one parameter because you only have male versus female. But then you also have age, for example, which has 70 parameters, or the power of a car, and so on. And we fit a specialized penalty for each one of them. And then, depending on what lambda value you choose, you can see which levels are fused for each variable. So this is, for example, the variable payment frequency. And you see, if you take a very small lambda, you basically get the GLM fit. And the payment frequency has 4 levels. One is paying once a year, then paying twice a year, 4 times a year, and monthly. And the one paying once a year is the reference category. So it's actually always put to 0, the parameter. And then you see when you increase lambda, then the 4 times a year and the 12 times a year are fused quite quickly, and it takes a long time for the other levels to be fused with the reference category. And you can also show that for age happening, but now you can see it starts very variable for a low lambda because we put a parameter for all ages. But then if you see it moving, you see that if you increase the lambda, you see that it makes clusters, and it actually forms quite nicely compared to a gum fit which was in the background. And of course, the interesting thing here is that if you look at like the final stages of fitting, more or less here, you see that there are here 3 categories. The bulk of the data is here, and then the older and the younger ages. The interesting thing here is there's a lot of bias in this fit. So that's something that you need to take into account. When you do this penalization scheme, you're actually trading variance for bias. So if you have clusters like these, you need to take into account if you want to get rid of this bias, you need to put these clusters again into a GLM, and then you will have get rid of your bias. So how did we then in the end decide on which lambda is the good value with respect to outer sample and in sample, with overfitting and underfitting? Well, we actually checked our data, our validation set of our data, and we took the lambda with the lowest mean squared error, and then we actually got from a GLM with 164 parameters initially to 40 parameters. So we got a lot sparser and got a lot more interpretation from our model. And this is actually how it looked like for the ordinal variables. So in the background you have the gum fit. The red lines are what comes from our penalized estimation, and then the blue lines is the re-estimation when we put the red clusters into a GLM. And then we have the same for nominal variables and the binary variables coming out of it. And to just finalize this, less is more. So if you want interpretation and sparsity in your model, you can use flexible regularization with different types of penalties. We're building an R package and working on the paper on this general framework. And apart from that, I just need to thank part of my sponsor, which is AGS Continental Europe, and then my colleague Tom Rankins, and you, the public, for listening to me. So if you have any questions, please shoot.
So, do we have any time? We're a little bit behind, so maybe one question, maybe? Anybody got any questions?
They're on the side.
Yeah, okay.
Thank you for the very nice presentation. Originally you said this has to be scalable, and that's why you cannot use GAM. And I don't quite understand. I mean, I'm not an expert here, but the high-dimensional people, even hasty and stuff, they advocate it. I mean, if you use a spline with only few degrees of freedom, in some sense, even a regression spline, then you also have only 4 parameters. And to me, it's very unsatisfactory, the dependency on age that you showed, and you know there is a bias. And I think a piecewise constant model for age is just kind of right. If you are over this age, your risk changes dramatically. It's so wrong.
Yes,
in some sense.
You're perfectly right in some sense. So the first part of your question is about the GUMs. GUMs are scalable to fit on larger data. That's definitely true, but they're not scalable for selecting parameters. Like if you do a best subset selection, it doesn't really work. That's what I meant by not scalable. And then the second part of your question about the bias, you're of course perfectly correct. If you prefer a GUM to a GLM, then what I'm doing doesn't look so nice. But what they need to do in an insurance context is they really need to have an interpretive model that they need to communicate to customers. And for example, if you use a GUM model for age, that means that every year your premium will be adjusted. And the customer just doesn't like that. And also to the regulator, you have to be able to say, okay, do I see for every age indeed an increase in my data set? So that's just a technical or like a practical thing in an insurance context that GLMs are still in some sense overused compared to GUMs. But that's the motivation why we use GLMs compared to GAMs.
Yeah, we got to move on now, unfortunately. Thanks for that.